And we are live! Boom, 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 boom. Another edition of Share Friday. Who's excited today? Hands up. We have Shaun in the bottom corner over here, taking us through some relatively light and digestible material, complex functions, and plotting. Oh, Jason wants to be added to the broadcast. Hey, Jason, welcome. Fashionably late. We can't hear you. You're on mute, but don't worry. Stinger, why don't you tell us a bit about?
I see the infinite versions. All right.
Yep, that's us.
Okay,
We're ready to go.
Can you see my Emacs?
Yes.
Your Emacs.
I just want to test that scrolling and stuff works. Can you see Wikipedia?
Yep.
Yeah, perfect.
So, I'm just going to give an overview quickly. There's going to be some math.
Quickly, if it's possible, can you make it slightly bigger? Like zoom in.
I can only take us out. I can do like this, but that doesn't help too much.
Control Shift plus or Command Shift plus in the browser.
Oh, you can just do your Command plus.
But I'm not sure about Emacs, but it's fine if it's just a.
You know what? It's just notes for me. Like you can read it, but it's more notes for me.
Super chill. Please zoom in on your browser.
On my browser. Okay.
Command plus.
See.
Yeah, there we go. Perfect.
Is that okay?
Yeah, that's perfect.
Okay, fine. Right, so there'll be some math to start off with. Then I'm going to explain my grapher, like how it works, and then I'll give a demonstration. That's just basically it. Okay, let's jump right in. I don't know if an hour is going to be enough. So what I'm going to do is I'm going to try keep the math as short as possible, but I don't know what math people know. So when I say as short as possible, I mean I'm just going to use words and definitions, assuming that you know them. If you don't know what they mean, please stop me, because it's pretty important to know what some of the words mean. Okay, the complex plane, right? So this is just an XY plane, basically, but the x-axis is the real number and the y-axis the imaginary number, right? So any point on that plane is a complex number. Okay.
Got it.
And I'm also just going to assume if there are no complaints that or people saying stop, explain more, that everybody understands.
Yeah, it's like 5 plus 3i or something as a complex number that can be plotted on the x and y axis. And for those who don't know, a very simple definition, a complex number I is the root of -1, because there's no negative number times another negative number that can equal.
Yeah, actually, to be honest, if you've never seen complex numbers before, this is going to be very confusing.
Rough, yeah.
I'm not even going to give a definition of complex numbers. Like we have to go a little bit beyond that. Yeah, but I think we all know. I don't know. I'm just going to keep going. Alrighty. So I want to talk about two functions because we don't have too much time. So I'm only going to pick two, and I picked these two. The one is the exponential function, but for a complex number. Generally, when you're talking about complex mathematics, you use Z to represent a complex number. So here, where you see Z, it just means a complex number. This is kind of similar to when you first learn about algebra and you use X's, and it's like, why did we pick X? And fucking who knows? So anyway, Z just seems to be the general letter used for complex numbers. So we're going to talk about the exponential function for Z and the cosine function for Z. I could pick sine or cosine, it doesn't really matter, but I only program cosine, apparently. So that's why I pick cosine. And the reason why I picked these two is because there is a really beautiful deep link between these functions, which is completely unobvious when you look at it through the eyes of real numbers.
Shaun, can I pause you quickly?
Yeah.
Do you mind giving a bit of an overview of what you're sharing? Like this is a program you built what is the context you made it for?
Oh, yeah. Okay. So back to the overview. Basically, I like when you do a course on complex functions, or when you do any math, right? It's very useful to visualize stuff. You know, when you're studying polynomials, you like to plot them on the Cartesian plane, you know, x and y, and see what it looks like. It's just very satisfying to see what things look like. And with complex numbers, you can't plot functions because you would need a 4-dimensional space, which we're fresh out of. And so it's hard to visualize the functions in the same way that you can view functions from a 1-dimensional space to a 1-dimensional space, like from the real numbers to the real numbers, like x squared or something, or all those real valued functions that we know and love. And so people have come up with some ways of visualizing complex functions, and they just weren't satisfying enough for me. So I tried to make my own one. That's basically what this whole thing is about. Sorry, thank you, Denim. I should have mentioned that earlier. So basically, I want to explain some complex functions and then show them on different complex plotters. And then finally, I'll show them on my complex plotter. So you'll see the difference between all of them. Okay. So let's go. What's the time here? Okay, 15 minutes. Let's go to cosine first. Cosine of a complex variable. Now, when you define functions of a complex variable, there are a few ways to do it. And a very common way is to take some definition in the real number space and expand it. So an example of cosine, okay, I'm also just going to assume that everybody knows what a Taylor expansion is. But if you don't, it's not super important. You can it's a way of writing a function in a power series, an infinite power series. So here is the Taylor expansion of cosine for a real valued variable x. And you can see here is the sum from 0 to infinity, and then you got this bad boy over here. And you'll see 2's everywhere. So, you know, the negative flips every n, and you'll see x is raised to the 2n, and there's a 2n on the bottom, right? And one way of defining complex cosine is you say, okay, we don't know, like when the guys were coming up with all the stuff, they didn't know how to do it, right? When I say coming up with all the stuff, I mean coming up with complex functions. So they were like, okay, one thing that we do know how to do in the complex world is we know how to multiply complex numbers together. So over here, you see x would be replaced by z in this instance. So we're trying to define cosine of z being a complex variable. And because we know how to multiply complex numbers together, this term over here, this x to the 2n, which would become z to the 2n, is actually easy to calculate. We know how to do that. So we can take this power series and we can say, well, just switch out x, put z in, and hey, we have some form of cosine in the complex plane, right? That's one way to do it. There are a couple other ways to do it, but I'm not going to go into those. I'm going to jump into now exponential function. Again, there are a few different ways, or maybe another thing I should say about these different ways of defining both these functions is that whichever route you take, you actually always end up getting the same theorems and the same results, which is kind of beautiful because it says that doing these expansions, you know, taking a definition in the real numbers and expanding it to the complex plane is a good way of defining complex functions. Right. Okay, so onto exponentials. Again, yeah, there's many ways of defining it. One way is similar to the cosine function with a power series. And I think this is it on the right-hand side. Yes, okay. So over here, you can, I'm not going to explain how to get this. It's again a Taylor expansion, but if you, also exp just means e raised to the power. So x means e raised to the power of x. And if you do a Taylor expansion of that function, then you get this power series over here. And similar to what we did for cosine, you just replace x with z because we know how to do multiplication in the complex plane, right? Well, I'm just saying, before they try to define all these functions, they first defined how to multiply complex numbers together. And I'm not going to go into that, but I'm just going to say, assuming that we know how to do that, then we can define these functions based on power series. And if we do that, wait, I'm a bit lost now. Come on.
Shawnee, did you do complex analysis with me? Was it the same year we did that course together? Is that where you learned about all of this when we were doing that course?
Yeah.
That was a rip snorter, that course. Wow.
Yeah, it was hectic. Come on, keep disappearing. There you go. Okay, so here is exactly what I said earlier, right? You take the x and replace it with the z, and then you get this power series in terms of complex numbers. Oh, I did forget to do something with cosine, but actually, let me just define this quickly, and then we'll get back to this other thing I wanted to say about cosine. And if you do this, there are a couple of really cool things. Like actually, this Wikipedia article is really quite nice in explaining how all these things fit together, and it does it quite succinctly. But I'm not going to go into too much. I rather want to show what the things look like using the graphs and the plotters instead of looking at all the math. But this stuff is seen in the math, right? So you can see the beauty in the graphs, or you can see it in the math. And just quickly, I just want to show you, if you were to take the exponential of it, so t here is real, meaning this complex number is completely imaginary. It lies only on the imaginary line. It doesn't have any real value. And if you do that and you expand the power series, so that's just putting z equal to it here, where I is real, and you start grouping terms together, you can in fact group them like this, right? Where you see here, all this crap is real, and then you have an I, which means all this crap is imaginary over here. And if you do that, and you try and come up with a formula for these infinite series, you in fact get the power series for sine and cosine, which is very, very interesting. It's like, why is sine and cosine appearing in the Taylor, the complex expansion for the exponential function? And that's kind of where things, this deep connection starts to get seen. So anyway, that's one way of defining the exponential function. And there's another way, I'm just going to show it briefly because it really is very cool. And this is using Euler's formula. Euler's formula is this thing over here, right? And you can see it certainly has exponentials and sines and cosines in it. But this was done before anybody tried to define the exponentials or the cosine functions for a complex variable. Like you'll see inside here, there's an ix. So sure, that is a totally imaginary variable inside there. But you can kind of say the function is e to the I and the variable is real. So it's not really a complex function, right? And over here, you can already see there is a link between exponentials and sine and cosines. So anyway, if you take this formula, you can say, well, what if we replace x with z, right? And then we would get cosine. We have a bit of a problem, right? We have, okay, we kind of know e to the I z is equal to cos z plus I sine z, but then how do we define cosine z and sine z? So there's a bit of a problem there. But if we go back to, where's this thing? Let me just find this. Over here. So every complex number, as you know, can be written as the real and imaginary parts, right? And when you do that, so you have exponent z over here, and that's equal to exponent x plus iy. And with exponents, you can, it's a common rule in the real numbers where, you have, I think it's pretty clear here, where you can split up the exponent into two separate entities. So you'll have e to the x as one of the multiplicands, and the other multiplicand would be e to the iy. And we know from Euler's formula that e to the iy is this cosine y and I sine y. So there are a couple of different ways of defining all this stuff. I don't know if I went too fast there, or if I didn't explain well enough, or if
that makes sense. Can you just go back to that last screen, Jason? So a complex number, z, can be represented by its real part and its imaginary part. So x plus iy, that's how we get from e to the z to e to the x plus iy. And then we know from Euler's formula that e to the iy gives us that other identity over there. Yeah, that makes complete sense.
Cool. And you're missing that plus in exponentiation is multiplication in
yes, exactly.
Yeah, exactly.
Nice.
Okay, but that, I mean, it's not too much of a problem if like some of that doesn't really make too much sense. What I want to show now are some graphs of these two functions. So here is a function plotter that I found while doing this course, because I wanted to try and visualize these functions, right? And basically how this thing works is, okay, here is the complex plane. I'll explain the circle in a minute, but where my mouse is moving now, that's the x-axis, that's the real line, right? And now where my mouse is moving now, that is the imaginary line, okay, or the y-axis in the Cartesian plane, basically. This is the unit circle. So that means if I have complex number here, so where my mouse is, that's a complex number. Every point in this plane is a complex number. Where my mouse is right now, the modulus, or the length of that complex number, is going to be 1. And that is so for all complex numbers on the circle. That's why it's called the unit circle, because unit is kind of analogous to 1 in mathematics. The colors are here because they help to view what the functions do. So the unit circle is also there to help view what the functions do. And you'll see right in the middle, there's a white. So that's the 0, okay? And the point of this, you see at the bottom here, I've just got Z, right? So that means I'm mapping Z to Z. It's basically like this, right? I'm just writing rubbish in here, don't look at the picture. But what this thing does is it maps Z to whatever you enter in this box. So right now I'm mapping Z to Z, so every complex number is going to be exactly the same complex number, so nothing moves. That's why you get the regular complex plane. But if I go e to the iz, then we see something kind of cool happen. The unit circle gets turned into a straight line. In fact, all circles get turned into a straight line. Wait, is that right? No, wait, I retract that statement. I can't remember exactly what some of the rules are around this.
You can't retract statements on a live stream. Sorry, Shaun. It's going to live on forever, dog.
But what's kind of cool here is that look where 0 is. 0 is all the way out on the left. So 0 gets mapped from the middle to like this whole line over here, right? Basically going up to infinity. I think you can zoom out here. I can't remember how to zoom out. Here we go. See, 0 gets mapped to all that stuff there, which is interesting. In fact,
Shaun,
I'm not 100%.
Go back to Z. I want to see how the grid looks. If the grid looks kind of, yeah, I can imagine it being all circles get mapped to a straight line. That visually looks correct.
And then
but let's not make claims that I don't know.
Yeah. Anyway, this is one way to visualize these things, right? And it's kind of satisfying. Like you see a bit of a pattern here. You see these kind of arc shapes, right? And it seems like some circles get mapped to straight lines. It looks cool. All right, now let's have a look at cosine. Now this looks very familiar to the cosine that we know and love in the real plane, right? Because we have this I don't know what to call it other than a cosine shape. Bending arc type thing. But
isn't it a sigmoid or something? Anyway,
sinusoid.
sinusoid, that's the one, yeah.
Yes. Yeah, I guess that's the better term to use. And it's kind of interesting that here 0, which used to be over here, kind of gets mapped to 2 different places. So there's 2 options, which you'll know means it's not a function, but I don't exactly know how this plotter works. I think what it does is it will, you know what, I'm not even going to try guess because it's going to take up too much time. Anyway, it's another way to look at this stuff. So I'm going to go on to a different way of plotting things, and that's looking at the real and the imaginary parts separately. So you take the function, all right, and then you find the imaginary part, and now you've got 2 numbers. You've got the x, sorry, you've got 3 real numbers, right? You've got the x which is the real bit from the imaginary number. Then you've got the y, which is the imaginary bit from the complex number. Sorry, the x is the real bit from the complex number. The y is the imaginary bit from the complex number. And now your z, which is confusing because now I'm talking about z in a different context, is the real part of the map of the function. All right. So no, I don't know if that made a lot of sense. I don't think I explained that very well. But what these type of plots are trying to do is they're trying to use 3 space, right? Our 3-dimensional space, and where each axis is a real number line, right? And then the base plane. I wonder actually if I can do something. See if this works. But the base plane, yes. Anybody know the formula for the 0 plane? No. God damn it, I can't remember it. Okay, anyway, you see this is 3 space, right? And you see this axis over here, that would be like one real number axis or one real number line. And this axis over here is another real number line. And then this third axis is also another real number line. And we know that the complex plane can be represented just using 2 axes, 2 dimensions of real number lines. And if we add this third, we can perfectly visualize this in our world, right, in 3 space. So how these other mappers or plotters work is that you assume anything lying on this base plane, right, the plane of these two arrows.
Isn't that just 0
X,
equals...
Yeah. 0. X is equal to 0.
X plus y could work, I guess. Or do you have to specify all of them? Oh, no, sorry.
X. So try y is equal to 0.
Equals 0.
Oh, we're being so stupid. Oh, obviously.
Yeah, like that. Yeah.
Okay. This is
hardcore math.
Anyway, this is your
too long.
This is your
we've
domain.
been programmers too long.
Yeah, I forgot about that. This is your base plane. So this is the domain, right, where your function takes from, and then it maps to another plane, right, which is why we can't properly visualize it because that would require 4 dimensions. So what we do is we say, okay, instead, we're just going to look at the real value. So for each complex number in this plane, we're going to take the function. So we're going to go exponential of e, of z or something. And then we're only going to take the real part of that because, you know, every complex number has a real and an imaginary part. And if we only take either one of those parts, that's 1 dimension. So we can perfectly represent that using this last axis in our tiny 3-space world. And if we do that, okay, I really was hoping this would work, but all it does is it just says initializing live version and it never does anything. It would be nice, but I found some other ones just in case. Okay, so what we're going to do now is we're going to look at the real part of the exponential function for a complex variable. So what we have here, like in the little graph that we were just playing with, we have an x and a y, right, plane, and that is your base plane, the domain plane, where your complex variable, the domain. I mean, I think everybody knows what I mean when I say domain. And the x-axis, the z-axis, is the real part of the result of the function. So we take the exponential, can't highlight this, but okay. Anyway, we take the exponential of our complex variable, and then we take the real part of that. And if you do that plot, you get this interesting looking beast. And if you just focus on where y is, you see over here, y is the complex, the imaginary bit, right? The magnitude of the imaginary bit of the complex variable. If that is equal to 0, then we have a purely real exponential function. And if you trace what the graph looks like on y is equal to 0, you see the exponential that we know and love, right? The plain old exponential function for a real variable. Does that make sense? Where I'm tracing with mouse. Can someone answer yes or no, so I know if that doesn't?
Yeah, everyone is saying yes with thumbs up.
Oh, I can't see you guys, right? I have one screen.
Oh, okay.
Sorry.
Okay, cool. Anyway, then we can do the same thing with the imaginary part, which looks very similar, actually. Yeah, so in this case, we have the plane is the domain, exactly the same as the last bit, but our z-axis is now the imaginary part of the exponential function. This thing is a heat map, which I think shows how high or how negative or positive the value is, right? So you can see there's this, I don't know what to call that, looks kind of like a bit of a mountain. Like there's the valley and there's the, I forget those bits. What are the bits in between two valleys of a mountain? Does anybody know the word?
A valley is the bit between two mountains.
No, if
Contours?
you have two valleys.
Contours?
No.
A saddleback?
No, it's called.
Isn't it called a saddle?
Yeah, something like that. I don't think it's a saddle, but anyway, whatever. This piece over here that my mouse is running over, right? That's the blue over there. And then the red is very negative. So the blue here, I think, is positive. And the red is negative. So then we have this alternating pattern. Well, these alternating hills, I'm just going to call them hills for lack of a better term. And we have a very similar pattern here, right? Yeah. So anyway, that's that type of graph for the exponential function. And I tried to find that exact same type of graph for the cosine function, and I didn't. I mean, these are just not as nice looking as the other ones. You know, you can see the little bits, for goodness sake. Anyway, look here, as if you take the real and the imaginary bits, you see they're also quite similar. One thing I should probably say is that where these hills go very quickly up, right? And those troughs go very quickly down.
Exponentially?
Yes. Wouldn't you think so? And over here, that's not the case, all right? These do stop. And another, like I pointed out in the exponential function for this type of graph, if you go to the point where here where y is equal to 0, and now this is not really making sense because it's completely flat at y is equal to 0. What? Anyway, you should, yeah, I don't, that's really weird. But if you go, That's why I wanted to find like exactly the same. You know what?
Oh, you can't even. I'm going to put some questions on you while we're looking at these colors. Question
Yeah.
1, does the color represent the angle of the complex number? Was the one question.
It
It represents.
might.
Okay.
You mean this bit over here, right? We're talking about this color.
Yeah.
So what? Okay, so that means, okay, so let's think about this. That means all this green bit, the angle is exactly the same for all these complex numbers, all right? Specifically for all the ones that lie on the y is equal to 0 line. So let's just take this here. If we go x is equal to 0 and y is equal to 0, that's the complex 0. And if we backtrace all the way here along the real line, right? I think x is real here. If we backtrace all the way here, so we keep y is equal to 0, but we decrease x to below 0, then the angle should stay the same, right? Because it's all the same color. So if color represents angle, then the angle should be all the same there. And I think if we go back to this graph and we do exactly the same thing, we go from 0, 0, and we backtrace negative x, then we see we run on one single line to 0, interestingly enough. So we go from this point, right? This blue point. So remember, if we just have Z, you see how these blocks, these little blocks are nicely positioned for us. And if we run along this blue line, we basically run from the blue to the white. So let's see if we run from blue to white. Well, yeah, I mean, in this case, that is exactly the same angle, the angle 0. But okay, so let's try something else. If we go from, let's go x is equal to -1, right? Because x is equal to -1 is this red little bit over here. And let's go up y, right? So we increase positive y. We should also have the same angle. So if I go back here, let's go cos. We start at x is equal to -1, which is somewhere around here. If I remember, we go up, we go positive y. Okay. Then we don't really trace against any particular line. We kind of just go, we go from somewhere in between the blue and the white, and we go towards green. So let's see if that gives us a straight line. I don't know if I'm doing this correctly, by the way. If anybody thinks I'm doing this wrong, let me know. So we start somewhere between here and we go up to there. No, there the angle's changing. So no, I don't think that the colors represent angle in this case. What I think it represents, as I said previously, is how steep the graph is, which kind of matches up with the picture here. So over here, it's red. Red could be very negative. Oh, look, our graph is very negative over there, right? Over here, blue means very positive. Oh, look, our graph is very positive over here. So that's kind of why I thought it meant magnitude rather than angle.
Okay. Interesting. We have another viewer, Jason Smythe, saying, from what I understand, yes, the color represents the angle. So I think we'll have to get back to everyone on this one, and there is justification. Shaun, can you maybe share the links of this, what is this, wiki natural exponential function? There's a couple people wondering what links you're looking at right now.
Yeah, sure. Right
Those
now
would be
or
super
afterwards?
cool.
Can I just share them all afterwards?
Yeah, you can
Or
share
them
them
look at them now, so I share them right now.
Yes, just send one or two now if you can. You can put it in the private chat here.
Is that the right place?
Yeah, it's the right place. I'll chuck it in our chat.
Oh, infinite screen.
Yeah, that's perfect. You can.
Oh God, did we lose everything?
Shaun's internet's not handling the infinite screens, yeah?
Hello?
Yeah, you're back.
Wait, am I back?
You can cruise away from infinite screens.
I wanted to... Okay, that's, I think, about is enough that I want to say about complex numbers, because we've got 20 minutes left. Let me just get onto my platter, right? But you can see, and to be honest, I'm not very satisfied with these things, because over here we see the graphs are actually different to these graphs. These kind of have very steep, what look like singularities, complex singularities, which is basically like a point of infinity. So I don't know. I'm not super satisfied, but to be honest, I just ran out of time before I could find the correct graphs. DuckDuckGo was not helpful enough. Anyway, let's go on to, okay, I think I just want to explain how my thing works before I show exactly what it looks like. So the first thing is, we have the domain and we have the image planes. What does that mean? The domain is just like where you take the variables from, and then the image is where they get mapped to. So you might have something like, Z gets mapped to f of Z, right? Some function of Z. So I don't know, maybe this is like e to the Z. So over here, this is the domain. And then over here, that is the image. So all the points over here, which is basically the whole complex plane, gets mapped to somewhere, and that's the image. And generally, well, with these functions specifically, it's the whole complex plane. So both the domain and the image planes are the entirety of the complex plane. I think I got that right. Yeah, which makes me really confused when I see singularities over here, unless I'm just looking at that wrong. I don't know, whatever. What was I gonna do? Okay. And the whole reason why we can't plot these things perfectly is because the domain and the image planes are both two-dimensional. So you would need a four-dimensional world in order to see them both. But what I thought is we have two different graphs, right? And you look at them kind of at the same time. And the first graph is, well, basically, we're going to be living in 3 space, all right? When I say living in 3 space, I mean very similar to, oh God, where is it? Yeah, similar to this, okay? So we're going to try and use our entire space. Well, when I say our, I mean like the 3-dimensional world we live in, that space, to visualize these functions. And the first thing we do, and it's very similar to this in the sense that we have this domain plane, which is like an XY Cartesian plane. And then we're going to have the image plane. Over here, the image plane is just taking the real or the imaginary parts. But what I do here is rotate. So first imagine that the image plane and the domain plane are exactly the same thing, which is exactly this. The domain plane and the image plane are occupying the same space, right? Except, you can't see them at the same time, rarely. They have a way of showing you them at the same time, which is that circle, or the unit circle, or the colors. There's a way of showing you what they look like, but you can't properly see them. But this is having the domain and the image plane in exactly the same spot. So imagine first that the domain and image planes are in the same spot, and then you're going to take the image plane and you're going to rotate it 90 degrees, and you're going to rotate it along the real axis. Okay, so that's the first graph that you get. If that's a little bit too hard to visualize, don't worry, because you'll see it in a minute. I just want to move fast because we're now running out of time. The second graph is you have the same setup, domain and image planes occupying the same space, and then you rotate the image plane 90 degrees about the imaginary axis. Okay. What's this? Yeah, but I've said that already. We're working in 3 space. Cool. Okay, and then now we want to know how to draw functions on these planes. Okay, well, in this world, in this setup. So the first thing you do is you start with, well, I banged this out super quick, so it's not very refined. It's quite a mess, actually. But what I did to simplify things is, instead of trying to map every number in the complex plane, or you couldn't with a computer. But instead of trying to map a very large section, I just took some small rectangle. And what it's going to look like, well, what the rectangle is a bunch of points, right? So it's a finite number of points. And I draw that on the plane by making little triangles with 3 points that are next to each other. All right, and that's important for rendering. I think this is how a lot of rendering stuff works, and that's how I render everything. Is at the bottom, it's just points, right? A finite number of points that are equidistant apart, and then I draw that on the plane by coloring in rectangles coloring in triangles that join neighboring 3 points. Okay.
Sure. What software or what programming language are you writing all of this logic in?
In Python, there's a framework called VPython.
Cool.
Let me finish this and I'll talk a little bit about that. Okay, and then we got to like think a little bit about what the coordinates are going to be. So you're going to have your rectangle, and then what I do is I apply the complex function to every single point in that rectangle, and then we get a resulting complex number, right? And now you plot that on the image plane. So yeah, I think it actually is just going to work better if I show and then explain with an image. Yeah, I was kind of saying, I'm going to come back to this because this is, I think, just too finicky. And I also added some color, similar to this thing. I added some color so you can see a little bit more. Okay, let's get right to it. This is the code that I wrote. It's really not too long. It was surprisingly short, actually. And I'm scrolling through it super quick. I mean, it's very like DIY at the moment, build your own adventure. I've been meaning to get back to this to make it better, but I haven't yet. So let's first look at the...
Can you make it bigger, please?
No, we're not going to look at the code. This is just me editing it so I can get the function that I want. Okay. This is all Python code, right? And this setup, or this framework, is called VPython, Visual Python. VPython stands for Visual Python, and it allows you to have these three-dimensional worlds. Now, I wrote this a few years ago, and VPython's versions have moved on, and their choice of like graphics, the underlying graphics network or whatever, or the underlying graphics software has changed. And so it was an absolute mission to get this to work, because my code doesn't run on their new framework or their new versions. And it also doesn't, like, how do I say it? It's not very smooth. It used to be smooth. It's now not very smooth. So in this 3 space, which you'll see is a 3 space soon, I should be able to move around. But it's not working. It's going to take a while. Do you see that it moved a little bit? I'm constantly moving my trackpad, but it's not really moving. And that's just because I don't know why. I mean, I think they knew there were problems. Here we go. Now it's smooth. So we can see here that we're in 3 space, right? And what I want to do quickly is zoom out and explain a little bit about these 2 different graphs. Zoom out to like 25. Okay, so these are the 2 graphs, and what we have on this left-hand side graph, so ignore the rectangle and the image there. So kind of ignore those shapes. In fact, to make the shapes a little bit easier to ignore, oh, where's my mouse gone? I'm going to try just get rid of that rectangle. This thing is the software is such a nightmare to use now. It used to be
Isn't that a square?
Broken. Whatever. Yeah, I mean, a square is a rectangle, no? Okay. Look, I'm getting rid of that stuff for now so that I can explain the space. Okay.
Okay. Got it.
do you see how there's the green bar on both graphs? Let me just, it's so fucking hard to navigate this. It's literally just freezing. I have to play with it. There we go. I have to play with it for a bit until it unfreezes. All right. So now we have like basically the same view in both graphs. This green bar is the real line for the domain, right? Same over here. The pink bar is the imaginary line for the domain, okay? So you can see that that plane, this green and that pink, the plane that is defined by those two straight lines is the same in both graphs, right? And that is the domain. That's the complex plane, but the domain complex plane. And the image plane is different in either graph. So in the left-hand side one, you see you take the plane and you rotate it 90 degrees about the imaginary, so that the image plane has the imaginary axes intersecting with one another, right? And then in the right-hand graph, or this plot, we see that we take the image, the domain plane, and we rotate it 90 degrees about the real axis, so that the real axes of both the image and the domain planes are parallel. They're the same axis. So you can see the light IM is the imaginary for the domain, and the light RE is the real for the domain plane, and the black is the image plane in both graphs. Does that kind of make sense?
Yeah.
Yeah. Makes sense.
Okay.
Like 90% sense.
Cool. And then it's so finicky. Give me something, bro.
So what did you say? The latest Python doesn't enjoy running the software anymore?
No, I have to get the old stuff because mine doesn't even work anymore. It complains about, like, I basically can't run my code at all. I'd have to make like major changes. I don't even know if I can have multiple windows in the new software. In the new version. So I have to try and get all this old crap working. It's even running on Python 2.7, which is a nightmare if you're using pyenv. You've got to delete all that shit and then install only Python 2.7. Bro, it was a nightmare. Let's not talk about how much of a nightmare it was to get this to run. Anyway.
Shaun, do you have a GitHub repo for all of this code? I'm sure we have some open source contributors who would love to help get it work.
Yeah,
could start a package.
Look, I've been meaning to get around to playing with this again and put it on some proper software, because I just did this as like an experiment to see what it looks like, right? Like you would ideally want like an edit box where you could enter your own function and it would do everything for you. Like the whole thing needs to be rewritten, not just modified. Anyway, so if we look in the domain pane in both of them, as I increase this slider, okay, it's a little bit hard to see, but you see there's that rectangle, and I'm increasing the size of the rectangle, right?
Yeah.
Yep.
That is the piece of the domain plane that I am applying the function to. So what happens is the program takes all the points here, and if you see there's little triangles, right? One in each square, one triangle is colored gray and the other is blue, of different hues, right? The different hues allow you to tell like which point gets mapped where, right? But the thing is, so in one of those tiny little squares, there are 4 points, and I apply the function to those points, and then I just draw the same triangle, right? So that you can kind of see where stuff gets mapped. And okay, now let's get into exactly how the coordinates work. So let's I know this is now a little bit, okay, this is actually too small. Let me rather break this and zoom in.
Can I ask a quick question, Shaun? This is a viewer question. How about the singularity of these functions? It seems not easy to visualize.
No, and I actually get divide by zero errors every now and then because, I mean, this program is simple, right? Like, it doesn't handle that shit properly. There are no singularities in these functions, right?
Okay.
the image and the domain planes they're perfectly mapped. What do you say? They're it's not a bijection. Are they both bijections? I think they are. Look, don't quote me on that. I can't quite remember the math exactly, but I know there are no singularities. In fact, maybe don't quote that on me exactly either. But I'm like 95% sure there are no singularities in these functions. Okay, so now we're a little bit more zoomed in, and you can see there that's the piece of the domain. Okay, I'm going to spend a few minutes trying to get this to rotate. Come on, guy. You can do it. You can do it. So I think let's just focus, because it takes so long to get this thing to move around. Let's just focus on the left-hand graph. Come on, guy. Ugh. Computer's not happy. Too much rendering. Okay, what I'm going to do now, I think let's focus on this bit here, is I'm going to, actually no, yes, let's do that. Okay, I'm going to extend the rectangle into the negative region of the real line. So you can see the rectangle coming through here, right? It's extending. It would be nice, look, it used to be able to scroll nicely, but it doesn't anymore. So what happens is, at this point over here, or let's take this point over here. When I apply the function, I have now 2 points. So I started off with 2 real numbers, and now I have 2 more real numbers. But I only have 3 numbers to show all of this, right? Because I'm in 3 space. So what I do is I want to show the 2 real numbers from the image. I want to show both of those for sure. But now I have 1 extra number to play with. Thought just occurred to me. I'm going to keep explaining. Okay, anyway. So I take 1 number from the image plane and I add it on there, right? And this is very similar to like when you have just a normal, regular, real valued function. Like if we're looking at the real exponential, you mapping a one-dimensional space to another one-dimensional space, but you take both numbers, right? You take the input and the output, and then you graph that. So you plot that point. The point that I'm plotting here, right? So I take my input z, my input complex number, apply the function, and I keep 2 numbers, right? The real and the imaginary part from the result. And then I take the real number from the point that I've fed into the function. And those are the 3 numbers that I use to plot. Whereas with the graph on the right-hand side, I do the opposite, right? I take each point. So over here, I take a point there, right? I apply the map or the function. I get my 2 points out, which is the real and the imaginary part of the mapped complex number. And then I take the imaginary bit, the imaginary number from the number that I fed into the function. So in that way, you'll see that on this left-hand graph, okay, it's, I guess, a little bit hard to see because the function decreases so quickly because it's an exponential. But you see how there's this little tail that doesn't exist. And as I start bringing my domain into that bit, the tail starts to get rendered, right? So you can see what happens is that this square, I guess it's more of a rectangle at this point, this rectangle gets wrapped around and squashed, right, into this little, what would you call this, like a super cone or something? Okay, I'm going to...
I'll call it like a hat.
Well,
so look like a sombrero.
We're out of time. Dude, to be honest, like, how much time can I go over? Is everybody saying?
Dude, there's no rush. We make the rules, so you can... I probably won't stick around for another 7 hours, but man, this is interesting.
Okay, yeah, so what's interesting here? Okay, what I'm going to do, let's look at the left-hand side first. Okay, the left-hand graph. And you see what I'm doing here when I move the slider, right? Is that I'm moving the rectangle down. You see the rectangle is now being increased down. And when I do that, right, let's start a little bit more up here. Can you see how this thing is I'm talking about the left graph now only, right? Can you see how it's kind of like a half cone now, right? I'm going to try and move around here a little bit so you can, it's going to take forever, so you can get a bit of perspective. But you see how it's like a half cone, right?
Yeah.
And what I'm going to show is that as I increase the rectangle down, this cone slowly gets built up, right? So you can see which bits get mapped to which other bits. So you see if I look from this point, then they occupy kind of the same distance. So you can see how some points get mapped to other points. And in fact, I can't scroll anymore. I've run out of, wait, there I can, I managed to do it. Kind of. I need to show something else interesting now, just now. But watch me first increase the size of this rectangle down, and then we'll see how that just draws the cone, right? And if you take a sneaky look to the right-hand graph, you'll see how that increases the spiral, right? You can see it starts drawing the spiral down, which is pretty cool. I don't know, I think that's pretty cool. Okay, what I want to show
That's very
now,
cool. I echo your
What I wanna
sentiments.
show now
Nice, dude.
is how to see your regular plain old exponential function using this graph.
Yes.
So what I'm doing here, look, I can't only take the numbers on the real line just because my program doesn't allow for that functionality. But what I'm going to do is I'm going to take a really small rectangle that is basically covering, you know, the real number line there. Okay. Now it's going to take a couple seconds to get this going. You can see on the right-hand graph, there's basically nothing, right? It's not really rendering much, much that you can see. Okay. What's that? That's the exponential we know and love. Right? Because you see on the green is the real number line from the image. The domain plane. And sorry, am I allowed to swear on this? Who cares? And then the black real. So we have the gray and the black. The gray being the image, the domain, and the black being the image. And the black real is just, you know, I've kind of I butchered that explanation. Okay, you see how there's two real number lines there, one gray and one black, right? One is the domain and one is the image. Well, if I do this, then we have a purely real look at the exponential function because I have a real input and a real output, right? And you can see the function. Look, it looks a little bit funky, but that's just because I couldn't get a perfect line on the real number line. I have a bit of a, just a really small rectangle. Anyway, that's really cool. And now I want to do that same thing on this graph on the side here, and I want to see what we'll get. I honestly haven't done this, so I'm pretty interested as to what it looks like. And then after that, I will just show, so this is the exponential, by the way. And then after this, I just want to quickly do exactly the same experiment with the cosine function to show you how these are mirror images of one another, these functions. Okay, let's squash this. Oh, my computer sounds like it's going to take off.
Shaun, don't worry. Our editing team, Jason Smythe, will put bleeps over all your swear words. So.
No. Okay, look here. So now what I've got is, look how beautiful that is on the right-hand side. Now I'll show you. You'll. I mean, I don't know. I know exactly what I'm going to see now because I know about the math and stuff. But maybe if you don't quite know what's coming up, then I'm hoping it's going to be a really wild, beautiful moment for you. I don't know. If it's not, then don't study math.
Can I do a drum roll? Tell me when I should start doing the drum roll.
Okay. But what I've done is kind of the 90-degree rotation of what I did earlier, right? We previously had a very thin rectangle on the real number line of the image number line, the domain number line. And now I have a really thin rectangle on the imaginary domain number line. And if I can just get this, okay, I lost it. Right. Let's try that again.
Quickly, while you're doing that, Shaun, there's some recommendations to try a tool called Penrose. Apparently, it does some pretty cool mathematical notation to some pretty awesome diagrams.
Oh, cool.
Something to check out at some point.
Cool. Thank you.
I wonder if it handles complex functions, and yeah, it'll be interesting to see.
Okay, we're almost there. Come on, guy. Be smooth for me. Oh, no, I've lost it. God. Okay. This is such a pain in the ass.
That suspense is unreal.
In fact, I think we were kind of at the view. We were a little
Yeah.
bit rotated, but we were kind of there. Can anybody see flippin' cosine here? Come on,
Yeah.
tell me.
Not yet.
Absolutely.
Oh, there we go.
Yeah. That's awesome.
Ah, there we go. There we go. Okay. Is that or is that my cosine? But
That's
look,
beautiful.
it's rotated because like with the software, I'm a little bit limited. So, you know, this line over here, the horizontal one, is not the domain, it's the image actually. So if everybody takes their screen and just rotates it sideways, you will actually see proper cosine. Well, you'll see it's a bit different, but it's basically cosine. When I say a bit different, I mean it's shifted. Yeah. Anyway, now what I want to do, let's just stop this thing. There's one more thing, and then we can be done. I want to show the cosine function. I hope everybody memorized what those things look like on the left and the right. But just to say briefly, like on the right, there was. Let me just show it again quickly. I won't scroll. I'll just. You see here on the left-hand graph, we have this cone, and on the right-hand graph, we have this like staircase, smooth staircase. I guess the thing that you use to drive into parking lots, actually, they usually look like that, kind of spirally, smooth spirally thing. And then, oh, also, if anybody's interested in how I actually plot this stuff, I actually use the expansions. So like, actually, no, I'm not going to get into that. We don't have time for that. Let's just do cursor.
But Shawnee, definitely put this puppy on GitHub and upload it.
Yeah, I mean, it's a bit of a pile of crap at the moment. It's just an experiment, right? Like I've been meaning for ages now to make a proper one. And hey, what's that? Some things have rotated a little bit, but we have a cone on the right-hand side, and then we have the spirally staircase on the left. Isn't that fantastic?
What a coincidence.
Yeah, I mean, it's just like what I'm trying to show here is that you don't see this kind of deep connection on any of the other graphs, right? If we go to this one, like there doesn't seem to be any link between this exponential, right, and the cosine. Whoops. Like they don't seem similar at all. And then if you go to these ones over here, like, okay, we see there's some hills and troughs. I guess they're kind of similar to this one. I mean, again, I didn't find the perfect. I'm not sure which one is right here. I'm pretty sure this is too zoomed in or something, like, because there shouldn't be singularities there. But over here, like, they don't really seem to match up, right? Like this just looks like a regular cosine, you know, but it's like cosine everywhere. And this looks like exponential, but it's exponential everywhere. You know, there's a positive exponential and then a negative and a positive, and you kind of think it just keeps going on like that forever. Whereas with this graph of way of looking at things, you can actually see these two functions, exponentials and sinusoids, like it's the same with sine, cosine, sine, they're just slightly different. You can see there's this really beautiful deep link. Like, in fact, they're mirror images of each other using these two graphs. You know, the left-hand graph is exactly the same, maybe just rotates it a bit, as the right-hand graph when you switch the functions. Yeah, so that's why I find this this plotter really useful. Yeah, I mean that's basically it.
Awesome.
There are a couple.
That's super
Yeah.
cool.
Yeah.
That's beautiful.
That was we had someone's okay. Yeah, Shaun. What can I say, dude? That was top notch, dude. Record
Cool.
number of viewers, record number of comments.
It was
10
great.
minutes Nice.
Yeah.
So I think we need to reach out to some professors around the world and get them to use your complex function plotter. I know when I was doing complex analysis, it would have been useful. Thanks for sharing the program back then, Shaun. I appreciate it.
I actually showed Jason. I showed Jason. Where were you?
You did. I don't know where I was. I didn't get. I missed out apparently.
Oh man. Yeah.
Sweet.
Yeah, anyway, what was that other thing that someone recommended? Penrose.
Yes, Penrose. You should try Penrose.
Cool. I'm gonna mark that down.
So check that out. Jason also says, awesome. Euler's formula is just beautiful. Love it.
Yeah, it really is.
That's true.
Nice.
Great
Cool,
comment.
guys.
Nice. Cool. Last thing before we go. I don't know if we have any recommendations for next Friday. Drop them in the comments below if you have any recommendations. Otherwise, it's going to be really cool, whatever we think of. If anyone has any topics, yeah, put it in the comments. Sweet. Get
Peace
out. Cheers, guys.
Perfect.
So.
Have a good weekend.